Hey guys, alright, we are on chapter 17 in this Giambattista book now. So, this chapter is all about electric potential, and so it's very similar to gravitational potential energy, or even, well, let's just leave it at electric or gravitational potential because I really like this image that it's giving you. This is how I always explain it to classes, and I've never had an image like this, so I thought this was really good. You can see this rock or meteor or whatever, it's falling towards the earth, and the higher you are, the higher gravitational potential energy you have. Well, similar to atomically, if you're thinking of electricity, if you take a charge and you pull it up here close to this positive right here, I can't write on it. Here we go. If you pull it up here close to this, it is not going to like to be by this other positive charge. So it's going to want to be, and it's going to be attracted to that negative charge. So the higher up, closer to the positive it is, the higher electric energy there is. Okay? All right, so electric potential energy and work. So if you recall, back when we were in energy stuff, we said that potential energy was equal to negative work. So think about it, like if you have, going back to this image, if you're pulling against gravity, right? Then, that's like positive work. If you start to drop that, it's going to go negative, it's going to go down, right? So potential energy is equal to negative work. So the amount of energy is taken from stored potential energy. Okay? So, similarly to gravitational potential energy, which we've already kind of established, both cases the potential energy depends on the position, okay? Not the path that they took to get there. Secondly, only changes in potential energy are physically significant. So, it says that we're free to assign the potential energy to be 0 at any point. And then for 2-point particles, we usually choose potential energy to be 0 when they are really far apart. Okay? And this is continued. So both gravitational and electrical forces exerted by one point on another are inversely proportional. So what does this mean? This means that, we had this equation a long time ago. We had universal gravitational equation. So we had this big G, and it was a constant, which was mass 1 times mass 2 over r squared. That's just the force. If we were wanting to find the potential energy, remember, potential energy is the same as work, and work was force times distance. So if we take this equation and we plug it in for force, and we multiply that by distance, which is r, and this was squared, by the way, then that's going to cancel that out, and you're going to be left with something like this. All right, so similarly, you can think about that on electricity as well. We have Coulomb's equation from chapter 16, so we still have to remember Coulomb's, but it looks very similar to the universal gravitation equation. So also similarly, if we do force times distance, then we get this equation. Okay? So this is potential energy for electricity. Okay, electric potential energy. So that's what that subscript E is standing for. Oh, I had taken this slide out. So that means that there's a few in here that shouldn't be in here. Sorry about that. Don't think that this is on the PowerPoint that is on D2L. So there's 115 slides. I have to take out a few. Okay. So here's our first example. This is, I don't know, I think it's a little bit interesting because it's showing an everyday thing, that that actually, we could think about, is happening as far as physics related and electricity. So this is showing that we've got a thunderstorm that's separating charges, and it's showing you what the charges are and how far away that they are. And it's saying first, what's the electric potential energy of the pair of the point charges, assuming that potential energy is equal to 0 when the two charges are infinitely apart. Okay, so if we do that, let's actually do some math here. We've got K Q1 Q2 over R. Remember, it's not squared because this isn't the force, this is the potential energy. And this is wanting us to find the electric potential energy. So if we plug in some of the information that we had, we know, of course, that K is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. One of the charges that it gave us was positive 50 coulombs, no micro or anything like that. And then it also gave us negative 20 coulombs divided by that distance that it gave, which was 8 kilometers, which is 8,000 meters, or 8 times 10 to the third, however you want to do that. And whenever you plug this into your calculator, you should get negative 1 times 10 to the 9th joules. Okay? Now, part B, I went ahead and I left this sort of explanation for you. It's saying, explain the sign of potential energy in light of the fact that positive work must be done by external forces in the thundercloud. So if you have a positive and a negative charge, they're going to fall towards each other, right? Which is going to be kind of like negative. It's going to be like negative. If you go back to this let me go back a couple of slides, more than a couple apparently. If you go back to this situation, that would be like negative work. And it's saying, why is this positive? Well, because the storm is actually pulling them apart. Okay, so that's what it's saying here, that the negative potential energy means that if those 2 point charges were infinitely apart, they would, their potential energy would decrease as they're brought together. As they're falling together, they would decrease, because that would mean like, it would be kind of like if you took a rock and you dropped the rock, the closer that it got to the earth would mean that it would decrease its potential energy. Okay, so in this case, it's saying that they are moving farther apart because there's an external force that's causing that. So that's why there's positive potential energy. Okay, so then you can also have situations where you have potential energy due to several point charges. That was just showing 2, but if you do have a case where you have several point charges, then you would have something like this, and you would just add those, for however many there were. And this is showing that the potential energy is negative of the work done by the electric field. So it goes back to that equation with negative work. Okay, so we've got an example that's showing you've got these 3 point charges, and it wants to know, it says to find the electric potential energy for the array of charges that are shown. So we've got charge 1, charge 2, and charge 3, and it's giving you the coordinates. So, you might not always get this picture. Just saying, like, it might just give you the coordinates and you'll have to put them on, a grid yourself. So keep that in mind. For the first part of it, though, we really need to figure out, like, the distance situation. So for our 1 and 2, right, we've got this at a diagonal thing going on. So we need to really figure out, like, we're going to have to use the Pythagorean theorem as far as that's concerned. So remember, whenever you're doing one that's at an angle like that, this should be similar to something that you did in chapter 16. You would do the y value, which is, in this case, 4, plus the x value, which is 3. Do the square root, and you should get 5. Okay, that's like a 3, 4, 5 triangle. And then the other ones are just x and y values, so nothing too crazy about those. So all you do is you take your equation for potential energy for electricity, and you do your K times, and I'm going to actually go down so that I have a little bit more room. So we have, for our first one, charge 1, it said was 4 microcoulombs, so 4 times 10 to the negative 6 coulombs. And then it also said that charge 2 was, what did it say charge 2 was? 2, yeah, microcoulombs divided by your distance from charge 1 to charge 2, which is 5. And those were in meters, by the way. Okay, and it's not squared. And then you just add the other ones. So plus, you've got 4. So now we're doing Q1 and Q3. So 4 times 10 to the negative 6 coulombs times negative, and charge 3 was, negative 3. And that's divided by this distance right here, so 3 meters. And I obviously have to go down more. So now we're going to do charge 2 and charge 3. So charge 2 was given at 2, positive 2 microcoulombs times our charge 3 again, which is negative 3, all divided by that y distance now, which is 4 meters. Okay, and you should get, whenever you plug all that in, you should get negative 0.035 joules. Okay, so you just kind of have to do all of them to one another. And that's how you would find the electric potential energy doing that. Okay, I'm going to stop this video because I'm not sure how long I've gone at this